Okay, guys, so let's go over the last two examples of lecture 5 about first order differential equations, first order linear differential equations, and these are the two missing examples of last session. Okay, so recall, let me remind you that in this for this type of differential equation, I mean for linear differential equation which looks like this. So we have the derivative of some function y with respect to a variable x, and we have two terms. The first one is a function p of x, which depends just on x multiplied by y, and this is equal to some function of x. So this is the general form for a linear equation of the first degree. Okay, so for this type of equations, this kind of equations, we can find an integration factor, if you recall the last session, and this integration factor allows us to write down the left hand side of our equation. The left hand side of our equation becomes equal to the derivative of some function. More precisely, it becomes equal to the derivative of a product function. So let me just write what is the basic idea. So we multiply both sides by the same factor mu, okay, and we want that that the left hand side equals the derivative of the product between mu and y. And this condition imposes a restriction on our function mu. And more precisely, this condition, you can read of the details in the notes, in these very notes. So you can find that the restriction that is imposed on this factor mu is nothing but the derivative of mu with respect to x need to be equal to p, to the function p of x times mu of x. And this equation has a virtue to be separable, and we can solve it explicitly by the method that we learned at the beginning of the course. And if you solve this equation, then mu can be chosen as the exponential of the integral of p of x dx. Okay, so we can take our integration factor like this exponential. Okay, so this is the idea, the general idea for solving linear first order degree differential equations. So let's apply this idea to our example. In our example, we have a differential equation given by this expression, but the problem here is that this equation is not a linear equation. So this is not a linear first order ordinary differential equation. So uh, what is the how we can solve this issue? So this is not a linear equation, but this only happens if you think of this y, this function y, as a function of the variable x. So if you think of y as a function of x, then in fact this is not a linear equation. Nevertheless, if we interchange the rules of x between x and y, then this equation becomes a linear equation. I mean, if you think of x as a function of y, so that our derivatives now looks like this, then this equation is in fact linear with respect to x and not with respect to y. In any case, this property of being linear with respect to x allows us to solve the equation explicitly. Let's see how this works. So, in order to write down this equation in terms of x, so as I said, we need to consider the derivative of x with respect to y, but we can obtain such kind of expression just by taking the inverse both sides of this equation. So you can take the inverse both sides, that is, you can divide 1 by this side, and this need to be equal to 1 divided by y cubed, and this allow us to rewrite our equation in an appropriate form. So you can take just the inverse both sides. So this is the first step. Here you take the inverse on both sides. And if you solve this equation with respect to the derivative of x, dx over dy, then as you can know, this is in fact a linear equation. So now our p is a function of y, and this p is nothing but the inverse of y, after writing correctly the equation. Okay, so we now have a linear equation, but thinking of x as a function of y. So this is not a problem. We can solve by the very same method our equation, and we can find an integration factor. In this case, the integration factor is an exponential, and the exponent is given, just as in the previous examples, by the integral of our function p, which is the coefficient in the linear term, which is this one. So our function p is the inverse of y, and the corresponding exponent in the integration factor is just given by the integral of that function. In this case, the integral of dy over y is just the natural logarithm of y, and the exponential is the inverse function of the logarithm. So that means that the integration factor for us is just is given just by the identity function. So mu of y is y in this case. Okay, so well, let's take this integration factor, mu of y equal to mu, and if you take this integration factor then and multiply both sides of our equation, so recall that our equation is this one, so this is our equation, and if you multiply both sides of this equation by y, which is the integration factor, then you obtain this expression. Now, the left-hand side of this equality is the derivative of a product, is the derivative of the product of y and x. So we can write this as the derivative of y times x, and the right-hand side is just the inverse of y squared. In any case, we can take the integral. So the integral on the left-hand side recovers the product y and x, and the integral of 1 over y squared is just given by a direct integral. So we can take directly this integral and the corresponding integration constant, and this allows us to solve the problem. So note that what we obtain at the end is an expression, an implicit relation between x and y. Namely, in this case, is the implicit relation y times x equals minus y to the minus 1 times a constant. So you can solve this as a function of y, that is, you can solve this implicit relation in terms of x, and if you do this, you can obtain an explicit form for the general solution. Okay, so the whole point of this example is to know that sometimes it is more convenient to think of the independent variable as y, and think of x as the independent, as the dependent variable. So this is the whole point of this example. Okay, so let's move on to the last example. So in this example, we have an initial value problem. So the differential equation of this initial value problem is given by the following equation. So note that this equation here is just a linear equation of the first degree. In this case, it is linear with respect to x. So we don't have the problem of the last example. Here we have just a plain linear first order differential equation as at the beginning of this lecture. Okay, so we have this linear equation and we have to solve the initial value problem. the corresponding initial value problem, and the initial condition is given like this. So the value of y over the solution at 1 need to be equal to some number, which is just y sub 0. Okay, so let's solve this problem. So again, the general idea is to find an integration factor mu in such a way that if we multiply both sides of our equation by the integration factor, then the left-hand side becomes equal to the derivative of a product, and the right-hand side is just a function of x, okay? So in this case, we need to divide, of course, the whole equation by x squared first. So if you divide the whole equation by x squared, we obtain the following equation, which is this one. So we divide by x squared, and this is just y divided by x, and this is equal to 1 over x squared times the sine function. Okay, so this is our equation, and this is p in this case. Well, this is the term which contains p. For us, our function p is just 1 over x. And this is the function that will appear in the exponent of our integration factor. So recall that the integration factor can be written down just in terms of this function p, and is given as the exponential of the integral of p. In this case, again, p is just 1 over x, and the integral is just the natural logarithm. And if you take the exponential of the natural logarithm, of course, you recover x, and the integration factor is, again, in this example, the identity function. So we can multiply both sides of our original equation, which is this one, by x, and if you if you multiply both sides by x, then you will obtain this new equation. But the left-hand side of this equality is in fact equal to the derivative of a product, is equal to the derivative using the product rule. As you can see, this is just the derivative of a product. On the other hand, on the right-hand side, we have the function sine of x divided by x. Okay, so now at the end, we can just take the integral on both sides of this equation. If you take into account the initial conditions, so we need to consider the integration limits. The lower limit is just 1, which give us the initial position for x, and we take the integral between 1 and x, which is the independent variable. So we can take the integral on both sides of this equation in order to solve the equation. But here we have the integral of a derivative, so we recover the product, which is x times y, minus, of course, 1 times y sub 0 because of the limits of integration. Okay, so this is our implicit relation between x and y. Okay, but note that the expression which is on the right hand side is an integral of a trigonometric function divided by t. So we have an integral, the integral of sine of t divided by t, and unfortunately we cannot write down this integral in terms of elementary functions. I mean, you cannot find some combination, some combination of some elementary functions like polynomials, rational functions, trigonometric functions, exponential, logarithms. You cannot find an expression for this integral. So this integral, of course, exists as an integral. We have no problem on the existence of this integral, but we cannot write down an explicit formula in terms of elementary functions. In any case, we can just take this as the definition of a new kind of function. So this new function, sine integral function, is by definition given by the expression, the corresponding expression. So we can just give it a name. We call it the sine integral function, or you can think that the implicit relation that we found at the end is just given in terms of the integral of something. So you can write down the explicit solution of our initial value problem like this. So this is a solution of the initial value problem, and is given in terms of this integral expression. So this is one possibility, or we can just take by definition this integral as the sine integral function. So the point that I want to stress in this example is that sometimes we cannot solve explicitly the integrals in terms of elementary functions. So as you can note at this point, in all these methods to solve differential equations, at some point we need to take the integral of something. So in some good cases you can solve these kind of integrals in terms of elementary functions, like in all the previous examples that we touch, but sometimes not. So this is not always possible, but well, there's no problem with that. Sometimes we cannot solve explicitly in terms of elementary functions. Okay, so this is for the two examples at the end of lectures 5, and just let me go over two more examples to end this lecture about linear first order differential equations. So in this first example, consider the following differential equation. So we have a linear differential equation of the first degree, which is this one. So we have the derivative of y over dx plus y equals 2 times the sine function. Okay, so first we want to show that for any pair of constants a and b, this function, this particular function y of p, given as a linear combination of the sine function and the cosine function, well, this y sub p is not always a solution of this equation. That is, if you take an arbitrary constant a and b, then the linear combination of sine and cosine with these two weights a and b is not necessarily a solution for this linear differential equation. So the first question is to find for which values of a and b the corresponding function y of p is indeed a solution to our equation. So we need to find the values, the particular values of a and b, for which this function is a solution. Okay, in the second place, we need to find the general solution. So we need to find the general solution of this linear differential equation, and as we will see, this can be done by taking an appropriate integration factor, just like in all the previous exercises. Okay, so and at the end, we need to show also, need to show or to find a particular solution which satisfy this initial value condition. Okay, so for the first question, let us just suppose that our function given by the linear combination of sine and cosine is a solution of this equation. So this just means that if you substitute this function into this equation, then we obtain an equality. Okay, so if you take the derivative of y of p with respect to the x and you add y of p, then you necessarily need to obtain the value 2 times sine of x. Okay, so this is the meaning of this statement that y of p is a solution. So let's suppose that for some constants a and b, we have indeed a solution, and let's see what are the restrictions that this impose onto the pair a and b. Okay, so let's just substitute y here, and let's take the derivative, the corresponding derivative, and then let's add this function y sub p. So in this case, if you perform the corresponding algebraic operations, at the end you will end with this equality. So the equality is that 2 times the sine function need to be equal to the difference between a and b times the sine function plus the addition of these two numbers a and b times the cosine function. And this impose some restrictions on a and b, of course. So the restrictions are given by this linear system of equations. Why? Well, because the coefficient, which is the partner here on the sine function, is need to be equal to 2. This is forced by the situation, and the coefficient which is the partner for this cosine function need to be equal to 0, because we don't have any cosine function on the left hand side of our equation. Okay, so now we have a linear system of equations and we can solve this linear system. So this linear system is very simple, so we can just take a look of these two equations and solve almost directly and find the corresponding values for a and b. And in this particular case, the value of a is just 1, and the value for b is just minus 1. So this means that if such a function y of b is a solution of our differential equation, then a and b are necessarily of this form. So a is necessarily equal to 1 and b is necessarily equal to minus 1. So this means that this function here, the difference between the sine and the cosine, is a solution of the differential equation. So this is for the first part of the problem. So now let's find the general solution and compare the answer of the first question with this general solution. So in order to find the general solution, we can, of course, consider an integration factor. So in this case, the function p of x is just the constant function q. The constant function 1. The function which is identically equal to 1. Okay. So our integration factor will be, of course, just the exponential function. If you perform the appropriate algebraic manipulation, like in all the previous examples, by in order to find this integration factor. So in this case, the integration factor is given just by the exponential of the integral of p of x dx. In this case, p of x is equal to 1, so this is equal to the integral of dx, and this is just e of x. Okay, so this is our integration factor. It's just the exponential function. Now, if you multiply both sides of the original equation by e of x, then the left-hand side of the equation becomes equal to the derivative of the product of the integration factor times y, and the right-hand side is just equal to 2 times e of x times the sine function. And you can take the integral of this on both sides of our equality. Okay, if you take the integral on the left-hand side, then you recover the product of e of x times y, and if you take the integral on the right-hand side, then you obtain the integral of 2 times e of x times sine of x dx. Okay, so if you remember from calculus 1, then these kind of integrals can be solved by something called integration by parts. So if you integrate by parts 2 times, so you need to take the integration by parts 2 times, then you will obtain at the end the corresponding value for the integral. You can see at the notes, and here are the whole procedure. But the point is that the integral can be computed directly, and in this case the integral is just like this. Okay, so note that the general solution, if you write down the general solution of the differential equation, this general solution contains the particular solution that we found in the first part of the problem, which is the difference between the sine and the cosine. And you have here a third term, okay, which is the term which contains the parameter of this one parameter family of solutions for differential equations. So the comparison between this general solution and the particular solution of the first part is just given by this last term. Okay, so this is for the second part of the problem, and the third part of the problem is just to find a solution, a particular solution which satisfies a particular initial value condition. But we can solve this directly just by taking into account that this is the general solution, and you can just plot the initial value, the initial values that we want in the expression for the general solution, and then solve at the end this equation in terms of C. In this case, in this particular case, the corresponding value for the constant function is just 2, and you can obtain a direct expression, an explicit expression for the initial value problem. Okay, so this is the last example about this topic about linear differential equations, and this is more qualitative. But nevertheless, it also need to be somewhat quantitative. So what is the question here? So we have a differential equation. In this case, this is a differential equation of the first degree and is linear. And the question is, if you draw, so recall that a differential equation can be represented geometrically as a direction field in in the plane. So if you write or if you draw the corresponding direction field corresponding to this differential equation here, then you can obtain a direction field, and the solutions of our equation will correspond with certain curves, right? So we have certain directions, and if you follow that directions, then our solutions are just curves in the plane. Okay, so the point or the question in this example is we need to show that all of these curves has the same asymptote. Namely, the asymptote here is given by the line y equal to x minus 1. So so this line is an asymptote for all the solution curves. So all the solution curves approach in the infinity at the same direction given by this line. So this is an asymptote for all these curves. So how can we prove that? So, well, we can just find the explicit solution because we know how to solve explicitly linear first order differential equation by the method of the integration factor, and we can solve this very easily by looking at the corresponding expression. So know that in this case the equation is just y prime plus y equal x. So p of x is just identically equal to 1, and the integration factor in this case will be given by the exponential of the integral of p, which in this case is just e of x. So our integration factor here is just e of x, okay? So if you multiply both sides of our equation by the integration factor, then you will obtain or you can rewrite the original equation like this. So the left hand side again is the derivative of the product of two functions, in this case the integration factor, which is e of x times y, and on the right hand side we have an expression which involves just the variable x. Okay, so here we can integrate both sides of this equation, and we can solve explicitly our equation. So for this example, we also need to use integration by parts 2 times, but if you do that, you find that the general solution is like this. It's given by a linear polynomial plus an exponential, which depends on a constant, which is the integration constant. And here it appears the factor y equal to x minus 1, and this means that this line is an asymptote for all the integral curves. So we can stop here, guys, and see you next Monday. Goodbye.